Hello friends, today I'm going to go over a directed graph, and this is an example of a directed graph, and then we're going to do a topological sort through this graph. So notice the vertices A, B, D, Z, F. This is a directed graph, so the edges connect, for example, only in one direction, A to C, B to C, B to D, D to Z, Z to F. So you could think of when is this used. This could be used for a build system. So this might be a dependency tree. So D might depend on B, F might depend on Z, Z might depend on D, F might depend on E, meaning that you could not build F before you build E, and you could not build E before you build C, and so on and so forth. So the strategy we use to sort this and determine the build order, we'll use a visited set and then a stack. So we could start anywhere. So let's randomly start at C. So I'll put C in the visited, and then the next operation is we have to go through and let me pause this. So we can start the topological sort of this directed graph at any point. So we randomly pick a point. Let's say our random point is point C, so it's vertex C. So the first thing we do is we add it to the visited set. So we add C to the visited set, and then we determine whether or not we add C to the sorted stack. So the question we have to ask ourselves is, have we visited all of the children in order to add C to the sorted stack? The answer is no. So we start by visiting the children of C. So we'll start with Q. We'll go down this route. So Q will add this to the visited set because Q is not in the visited set. From Q, does Q have any children? Yes, Q has one child, R. So we will add R to the visited set. Now, does R have any children? No, R does not have any more children. We can see that there's no more edges to any more vertices from R, so we can consider R sorted. So we'll add R to the sorted stack, and then we'll go back. So we'll go back to Q. So Q, are there any more children of Q to visit? Yes, or actually no, there's no more children of Q to visit. So Q will move to the sorted stack, and then from Q we will go back to C. Does C have any more children to visit? Of course, it has E. So we'll add E to the visited set because E is not in the set yet. E has children to explore, F. So F has not been visited yet, so we will add F to the visited set. Does F have any more children to explore? Nope, it does not. It is considered sorted, so we'll put F here, and then we'll go back to E. E has been visited. E has no more children, so E will be added to the stack, and then we'll go back to C. C has no more children. We've visited Q and E, so we will add C to the stack. So now we have totally explored this part of the directed graph, and we'll randomly pick another place. So we'll choose to go with, let's say, A. We will add A to the visited set, and then does A have any children to visit? Yeah, A does. We'll go down this route to V. So we'll add V to the visited set because it's not in the set yet. And then we will ask, does V have any children? No, V does not have any children. So V will be considered sorted. So we'll go back to A. A has been visited. A doesn't have any more children. Yes. C has already been visited, so we can consider A totally visited. So we will add A here. Now we'll pick another portion of the directed graph. So let's say we go to B. So this is, of course, as random. So B will be added to the visited set. From B, we'll explore the children. C has already been visited. We'll go to D. D has not yet been visited. D, does this have any children? Yes, it does. D has Z. So we'll add Z to the visited set. And then Z, does this have any children? F. F has already been visited. So now we can consider Z fully visited. So we'll add Z here. We'll go back to D. D, does this have any more children to visit? Nope, it does not. So D is now considered fully visited. And then going back to B, B has explored D, it's explored C, so we'll add B to the stack. So our final answer will be B, D, Z, A, V, C, E, F, Q, and R. So let's see if this makes sense. So can we build B first? Does it depend on anything? No. Can we build D next? It depends on B. B's already been built. Z depends on D being built. And then we go to A. A, can this be built? A does not have any dependencies, so A can be built. V depends on A. C both depends on A and B. A and B have already been built. Then we'll go to E. E depends on C being built. C has already been built. F depends on both Z and E. Z and E have already been built. Here's Z, here's E, so F can be built. Q depends on C. C has already been built. And then R depends on Q. So that is our sorted graph. That's it. It's that easy. Now I'll take you through the code. Right now I'm going to show you the code in Go, my implementation of the topological sorted graph. So I'm going to jump into main. And a few important things to call out. I import container list and format. This directed graph here, this is a representation of what I intend to build, and that was just what we went over in the video part of the exercise. Most of this work that is done here is just setting up the graph itself. So the graph is basically the nodes represent the vertices. The vertices are a collection of strings. So you could think of the strings as the vertexes that in the graph, like A through Z. And then the node up here, this shows whether it tracks all of the edges of the graph. So and then we just simply map it to true if there is in fact an edge between 2 points. So the new graph simply creates a pointer to a graph, and then it makes an empty set of nodes. Adding a node, we check to see if it contains the node before we add it, and then we add it to this set of nodes using the name. So we'd pass in, like, for example, vertex A or vertex B, and it would just be set to this group of nodes. And remember, there's no in this node right now, and right here at this point, there's no edge. So in order to add an edge, we simply check to see whether the from node is in the set of nodes. If the to node is in the set of nodes, if it's not, we return an error. And then we just simply map the from node to the to node using that bool that I talked about earlier. So this maps, this creates the edge, so the from A to B, and then we just simply say A to B, and then it would, in this lookup, it would just simply return true. Of course, we will initialize the graph in main, and then I'll come back to main after I show you what the initialization of the graph looks like. So I have a slice of strings. These are all the vertices. I simply loop over that, add the node, and then I write all the edges, and that again builds the graph that I took I explained in the last part of the video. So main, what we do here, my decision I made here was to track the visited vertices. We'll use a map of string to bool. So for example, if we visit A, we would simply we'd pass in A to true, and we know that we had visited A. The sorted stack uses that linked list. So what we start off doing is we'll range over all of the nodes of the graph. If the vertex is already visited, so for example, if we visit A twice, we would just continue on with the loop. And then we call this top sort with the vertex we're exploring. So keep in mind, this would be something like string A. The stack itself, so the stack is the linked list of sorted it's the sorted stack, and then the visited map. So this is the topological sort function. Pretty simple. First thing it does is it marks the vertex we're at as visited true. Next, it will look at the particular vertex we're looking at, and then it will range over the children. And then if the child is already in the visited map, it will continue on with this loop here, looking at the next children. And then to explore the children, we simply recursively call this top sort function, passing in the child. So after we've explored all the children and so on and so forth, we take the vertex we've explored. It's fully explored after we've explored all of the children, and then we push to the front of the linked list that particular vertex. So then at the very end, we've got a sorted list or a sorted linked list of visited vertices. So I had to just create a way in which we'd loop over that linked list and then print it out. So you could see here, I call next until there are no elements of the linked list, and I always look at the front of it in order to iterate over the stack. So let me just quit here, and I'm going to run the script, and you can see that this represents the problem I just explained. And then you could see that A would be built first, F would be built last, F depends on A, E depends on V being built, and so on and so forth. So that's it. Thank you for watching, guys. Goodbye.